Hi everyone, let's look at energy balance for a constant pressure. For a constant pressure on expansion or compression. So the first thing you need to understand, for constant pressure, expansion or compression, we have this equation that is valid. This is the boundary work done. This is the enthalpy, and actually it is the change in enthalpy, and this is actually a very interesting process, which is the change of energy. The change of energy. This is the change of energy, and this change of energy can be the potential energy in principle, but not the kinetic energy. So this can be what? U2 minus U1. This can be what? H2 minus H1. So this is what it is. So now, to begin with, you have to start from this expression, which is what? The change of energy for a system, which is what? Energy in minus energy out equal to what? Change of energy for the system. And you know for sure that this energy in and energy out depend on the system. If you look at the system, the energy in can be heat. The energy out can be work, which we can call other form of energy. And because that other form of energy can be done, this work done, other work done can be what? Power or work done by a shaft. And then we know that we have a unique work done, which is the work done due to the boundary, and this is the boundary you see here. So this is what we'll be talking about, which is what? The boundary work done, which is equal to what? Integral from point 1 to 2, that is the boundary work done, which we all know. It is a work done that is obligatory, it is mandatory, it is in your formula. But this other form of work, which can be done by a shaft, it depends. If we have a shaft in the system, that work done exists. If we have, it can be done by a shaft, it can be done by even an electric system. It can be done by even an electric system. So that other work done will be defined based on the problem. That's why they said other work. Why this is the boundary. And because work is done, it's a negative energy, because energy is removed by the system. Remember, when you do work, you lost energy. Because you lost energy, we have a negative work done. That's why you see minus sign, and minus sign exists, because there is a negative energy due to the loss of work. And this is just the change of energy for the system. U2 minus U1. That's what it is. And that change of energy can be kinetic, it can be potential, it can be internal energy, but it is that change. And now, if I want to organize this equation by taking work in the other side of the equation, I'll have what? I'll have a scenario whereby I have heat minus work, which will have order. And because we've spoken about this net is the boundary work done, which is what? PO V2 minus V1. That is the boundary work done. Remember, this is the boundary work, and this is the change of internal energy for the system. And if we organize this equation by taking this boundary work and to the other side of the equation, we're going to have this and this, and this is equal to what? H2, which is enthalpy, H2 minus H1, that is enthalpy. And it is true to say that enthalpy is equal to what? In energy plus pressure times volume. So that is the meaning of enthalpy. So whenever you see enthalpy, we can say that it was energy plus pressure times volume. So this is volume, this is pressure, this is energy. So all of this is equal to what? Enthalpy. So that is enthalpy. And therefore, because this is the boundary work and this is equal to what? It's equal to U2 minus U1, which is equal to what? Change of energy for the system. We saw that the value for heat minus the work, which is just any other work, as I explained. It can be powered by the shaft or electric energy given to the system. It's equal to what? It's equal to U2 plus P2 V2 minus U1 plus P1 V1. So this become H2 minus this become H1 . So that is the implication. And therefore, we may say that heat into the system minus work by other form of energy is equal to what? Is equal to enthalpy. This is the change of enthalpy, which we will call change of enthalpy. So that is the formula you see here, and that is how the formula is derived. And whenever you see enthalpy, it is a knowledge of what? Enthalpy is a knowledge of what? Change of internal energy plus boundary work. So this expression, change of energy, which is what? Change of energy plus boundary work is equal to what? Change of enthalpy. And that's what you see. So be able to implicate or involve that. Whenever you see an expression of what? Heat minus work, any form of work, equal to what? Change of internal energy, change of energy plus boundary work. You can equally say that the heat minus the work by other form of energy, is equal to what? Change of enthalpy. Change of enthalpy, which is equal to what? H2 minus H1. And we can go back to chapter 4 by using the property table, because we have to be able to know that this is the substance, in that case is water, and this is pressure. If pressure is 0, work is 0, we talk about a constant pressure expansion, because pressure was equal to 0 and work was equal to 0. Therefore, we can say that process was a constant pressure, and that's why you see the pressure here was equal to what? Constant. So that is how we define that case. So for expansion, when we say on restrained expansion, the heat into the system is equal to what? Is the change of energy, which is equal to what? The mass with respect to what? U2 minus U1. That U2, this is the internal energy. This is the internal energy. Internal energy at point 2, and this is the internal energy at point 1. So that is the unrestrained expansion formula. So whenever you are told that the problem is an unrestrained expansion, just know that the heat into the system, this is the heat into the system, is given by a formula, which is still equal to what? The change of internal energy. Change of internal energy, which is equal to what? This is the mass of what? Of substance, times what? U2 minus U1. I've already spoken U2 internal energy at point 2 and U1 internal energy at point 1. And this internal energy, we can get them from what? From the property table, from the fluid, from the working fluid, which can be water, which can be gas, which can be propane, which can be refrigerant, and that's how we determine the energy into this system. And that is what this is actually, the energy into this system when the system is experiencing unrestrained expansion. So this is the energy into the system formula, which I already explained. So right now we're going to look at one example, and then you will try the other example in class.